An oscillator consists of a block of mass 0.5 kg connected to a spring. When set into oscillations with amplitude 35.0 centimeters, the oscillator repeats its motion every 0.5 seconds. Find the period, the frequency, angular frequency, the spring constant, and the maximum speed. Okay, now let's get started. First thing first, let's find the period. Now we're taught to say this oscillator repeats its motion every 0.5 seconds. And also period is simply the time taken for an object to complete one full cycle. So that means that when an object repeats its motion back to its starting position, what we obtain is the period. So the period is this time that we are given, which is 0.5 seconds. So there's no calculation that is required for the first part, just to get the same value that is in the question. Now we go to B. We're looking at the frequency. Now frequency is the inverse of time, which is 1 over the period, meaning that we're going to have 1 over 0.5. Now when you compute this in a calculator or just by doing it, we get a 2, and the units are simply hertz for frequency. That's how you answer the second part. Alright, now we go to the third one, where we have the angular frequency. Now by definition, angular frequency is given as the rate of angular displacement, which is 2 pi. Now rate means that we're dealing with time, which is the period in this case. So we'll have that angular frequency will be equals to 2 times 3.142, which is the value for pi, over the period, which is 0.5, the same one that we obtained from part A. Now when you multiply in the numerator, you get something like 6.283. Then you divide by 0.5. When you divide, your quotient comes out to be 12.566. And this is angular frequency. The units are simply rads per second. Sorry. Okay, we now go to part D. Now for part D, we're simply looking at the springs constant there. Now we know to say angular frequency can also be calculated as the square root of the constant k over m. So it's the same constant we're looking for. Now we're going to make it subject with the formula, that is by first getting rid of the square root by squaring both sides. So the square root cancels the root, so it gets angular frequency squared equals to k over m. Upon making it subject, we get k to be equal to angular frequency squared multiplied by the mass. Now our k, which is a spring constant, will simply be equal to angular frequency, the same one we obtained in C, just that we're going to square this time around, multiplied by the mass, which is the one given in the problem, which is 0.5. Then when you compute this on a calculator, we simply get our k to be equal to 78.95. Now let us obtain the units. Now we have that since this simple harmonic motion is caused by a restoring force, which is directly proportional to the displacement, so our force will be equal to ky. Now when we divide both sides by y, making k subject to the formula, we obtain k to be equal to force over displacement, and this means that k will be Newton for force and meter for displacement. So these are the units for the same constant we're looking for. So upon finding the values, we say that spring constant will be equal to the value then Newton per meter. That's our answer. We now go to the last part, which is E, while looking at the maximum speed. Now for a simple harmonic motion, the maximum speed is the speed obtained by a particle at mean position, and this is given as the amplitude multiplied by the angular frequency. Okay, so that's how you obtain maximum speed, which is simply at mean position. Okay, now amplitude from what we have in the question is given as 35.0 centimeters. We need to change this to meters since these are the SI units. When we divide, we get 0.35 multiplied by the angular frequency, which is 12.566. Then when we do everything, we're going to get 4.4 as the answer. So we have 4.4 meters per second as the answer. Thank you very much for watching this video.